Welcome everybody to this presentation. I'm going to be presenting this paper on irregularity integral Sombor indices, theory and chemical applications. This is a paper with professors Ricardo Abreu-Blaya, José Manuel Rodríguez, and José Manuel Sigarreta from Universidad Carlos III de Madrid in Spain and Universidad Autónoma de Guerrero in Mexico. Before starting with the paper, let me introduce you some concepts that are going to make the presentation more easy to understand. First, a topological index is a graph theoretic invariant which reflects the structural features of a molecular graph. What do we mean by a molecular graph? Well, a molecular graph is simple graph representing the carbon atom skeleton of an organic molecule, where the vertices represent the non-nitrogen atoms and its edges represent the covalence bond between the corresponding atoms. In case someone doesn't know, a graph is simply a structure used to model a pairwise relationship between objects, and it's composed by two things, the vertices and the edges. In this case, the vertices are represented by these atoms, and the edges are represented by these covalent bonds between the atoms. Okay. Why these topological indices are useful? Well, because they can summarize some structural properties of the molecules into some numerical value. In particular, we are going to be interested in the vertex-degree-based topological indices that play a very important role in chemical graph theory, as we are going to see later on. Our main interest in this paper is this type of topological indices, as I said, in particular the one that is called Sombor index, which has been recently introduced by Professor Ivan Gutman, and I'm going to talk about this index a bit more in a moment. A simple example of why these topological indices are useful, just to put you an example, although only about 1,000 benzoate hydrocarbons are known, the number of possible benzoate hydrocarbons is extremely huge, and therefore to model their physicochemical properties, it's very important in order to predict the properties of unknown species. These topological indices allow us, since they are very correlated with these chemical properties, allow us to model this and predict these properties of potential unknown species. Okay. With this said, let me introduce you the Sombor index and some notation. Through this work, G is going to denote a simple connected graph, finite. This is simply a graph where the vertices are finite and it's connected, meaning that there is not a single vertices that is not connected to any other vertex, okay? Meaning that all the vertices are at least connected to other vertices through one edge. Where in this notation, B is going to denote the number of vertex and E is going to denote the number of edges. Then we have the degree of a vertex that we are going to denote by the letter D. And if there is an edge from a vertex U to a vertex B, then we are going to indicate this by UB or BU. Okay. With this set, we can go to the Sombor index, which is as follows: simply the sum over all the edges connecting two vertices, UV, of what the square root of the degree of vertex U to the power of 2 plus the degree of vertex B to the power of 2. So each edge UV is represented by a point in the two-dimensional metric space, such that its distance is to the origin is precisely this square root of x to the power of 2 plus y to the power of 2, which is the degree radius of UV. So summing up over all these edges, we get the Sombor index. Okay. So in this paper, we are going to continue with the study of topological indices from a geometrical point of view, proposing studies two families of topological indices, the first and second irregularity integral Sombor indices. Okay. We are going to discuss the application of these indices in quantitative structure property relationship and quantitative structure activity relationships, research, which are two methodologies that are widely used in computational chemistry to model the properties of molecules. And in particular, we are going to be interested in the properties of the enthalpy vaporization, which is simply the amount of energy that is needed to vaporize a mole of a liquid at a given temperature, and the standard enthalpy of vaporization, which refers to the enthalpy change when a mole of a liquid is vaporized at a standard condition. These are going to be the two properties that we're going to check the correlation with our irregularity indices. With this set, let me introduce you some new classes of integral irregularity indices. and some more notation. We're going to say that a topological descriptor T is an irregularity index if the following is held. First, that the T is bigger or equal than 0 for every graph G, and that T is equal to 0 if and only if G is a regular graph. A regular graph is simply a graph in which all the vertices, the degree of all the vertices has the same value. Meaning that all the vertices are connected to other vertices by the same number. So there are two quite famous irregularity indices that are called Albertson index and the misbalance Deg index, which are as follows. The Albertson index is simply the sum over all the edges UV connecting vertices of what the absolute value of the degree of vertex U minus the degree of vertex B. And the misbalance index is simply the sum over all the edges connecting two vertices of the absolute value of what the degree of vertex U to the power of 2 minus the degree of vertex B to the power of 2. As you can see, these two indices fulfills the two properties that I said before. These the two indices take value 0 if and only if the degree of all the edges of all the vertices are the same for all the vertices, right? So these indices at the end of this irregularity index at the end is just a measure of how irregular is the graph. Okay, and several of these irregularity indices has been shown in the literature that are very correlated with these chemical properties that I said before, the enthalpy of vaporization and the standard enthalpy of vaporization in the set of octane isomers. And this is what we are going to do. We're going to build two new integral irregularity indices, and we are going to check the correlation with these chemical properties, okay? Let me introduce you to some more notation and some objects that are relevant. We're going to say that the set of function G is an irregularity admissible if for each function G of alpha is a rectifiable function and the following property is satisfied. What property that for each positive integers A and B, there exists a unique alpha such that G of A is equal to B and G of B is equal to A. With this, we can define the two following objects, H of G1, which is simply the integral in the interval of the minimum value between A and B to the maximum value between A and B of the square root of 1 plus G prime to the power of 2. This is simply the length of the graph, okay? And the second object is this HG2, which is going to be the integral again in the interval between the minimum value of A and the maximum value between the minimum value of A and B and the maximum value of A and B of G of alpha, which is simply the area under the graph. So with these two objects, we're going to build the irregularity Sombor indexes, which are as follows. The irregularity Sombor index 1 is going to be the sum over all the edges connected to vertices UV of what of this first object, the length of the graph. So we are going to be summing up over all the connected edges, all the edges connecting to vertices, the length of the graph. And the second irregularity Sombor index is going to be the sum over all the edges connecting to vertices of the second object, the area under the graph. With this set, let me go to the theoretical results, and then we're gonna see the empirical results. In the theoretical result, basically what we're going to see is how these two irregularities Sombor index that we built are linked to these two well-known and famous irregularity indices, the Albertson index and the misbalance index. And then we're going to see also how we get, for some particular functional forms of the set of functions G, that we get some nice closed form solutions for our irregularity indices that we can easily put into a laptop and then allow us to perform these empirical checks with the chemical properties. So let me start. If G has this particular functional form, alpha minus x, and alpha is bigger or equal than 2, then what we are going to get is that the irregularity Sombor index 1 is going to be equal to the square root of 2 times the Albertson index. And the irregularity Sombor index 2 is going to be equal to 1/2 times the misbalance index for every graph G. Okay, this is the first result, which is not very general, but is a result we get. Now we get a theorem that is more general, which is that if the set of functions G is an irregularity admissible set of functions, whatever is this set, then the irregularity Sombor index 1 is an irregularity index, and we can check that the irregularity Sombor index 1 is going to be bigger or equal than the square root of 2 times the Albertson index for every graph G. And furthermore, if G of alpha is not increasing for each alpha, then we are going to get that the irregularity Sombor index 1 is going to be smaller or equal than 2 times the Albertson index. Okay, so we're going to get like some boundaries for irregularity Sombor index if these properties are fulfilled. Then we have again that if G is the set of functions G of alpha is an irregularity admissible set of functions, then the irregularity Sombor index 2 is an irregularity index. And furthermore, if G of alpha is a non-increasing function for each alpha and G is a graph with a maximum degree delta, capital delta, and a minimum degree delta, then what we have is that the irregularity Sombor index 2 is going to be bigger or equal than delta times the Albertson index, and it's going to be smaller or equal than capital delta times the Albertson index. Also, this irregularity Sombor index 2 is connected to the misbalance index in the following way. If G of alpha is a convex function for each alpha, then we are going to get that the irregularity Sombor index 2 is smaller or equal than 1/2 the misbalance index for every graph G. Okay. Now we are going to see that for some particular functional forms of this set of functions G, we are going to get some nice closed form solutions for the length of the graph and the area under the graph that will allow us to compute easily the irregularity Sombor index that we have built. Given P be strictly bigger than 0, the following set of functions, G of alpha with the following functional form, alpha to the power of P minus x to the power of P, altogether to the power of 1 over P for every value of alpha bigger or equal than 2 or to the power of 1 over P, is irregularity admissible. Furthermore, given positive integers such that A is smaller or equal than B, then we can compute the length of the graph and the area under the graph in the following way. The length of the graph is going to be equal to this first object here, and the area under the graph is going to be equal to this object in the second line here. Then summing up over all the edges connecting to vertices, we can compute the irregularity Sombor index 1 summing up this expression here, and similarly summing up over all the edges connecting to vertices, we can sum up the second expression and get the irregularity Sombor index 2. Similarly, the following set of functions with the following particular functional form, G of alpha equal to the square root of alpha to the power of 2 minus x to the power of 2, such that alpha is bigger or equal than the square root of 2. Again, is a irregularity admissible. Furthermore, given some positive integers such that A is smaller or equal than B, then again, we can get two nice closed form solutions that are very easily to compute with the laptop and allow us to compute very easily the regularity Sombor index 1 and 2. In particular, for this particular set of functions, we get that the length of the graph has this particular functional form in the first line, and the area under the graph is this has this particular functional form. And again, summing up the first expression over all the edges connecting to vertices, we get the irregularity Sombor index 1, and summing up the second expression over all the edges connecting to vertices, we get the irregularity Sombor index 2. Again, continuing with this type of theorems that we get, given some P strictly bigger than 0, if we define the continuous function G of alpha for each alpha bigger or equal than 1, as the following function, alpha over x to the power of p if x is bigger than strictly bigger than 0 and smaller or equal than alpha to the power of 1 over p plus 1, and alpha over x to the power of 1 over p if x is bigger than this number here. Then the set of functions g is irregularity admissible. And again, we can compute for some positive integers a and b such that a is smaller or equal than b. The length of the graph that now has this particular functional form, that even if it looks a bit ugly, again, is very easy to compute with the laptop and allow us to compute the irregularities on board index in an easy way, the first irregularities on board index in an easy way, and then allow us to compare it with the chemical properties we want to study. And then the second and third line are the expressions for the area under the graph that allow us to compute the irregularities on board index 2. If p takes value 1 and if p takes a value different from the to 1, then we get these two different expressions for the area under the graph. But again, allow us to compute very easily the irregularities on board index 1 and 2. With this said, let me go to the empirical applications. We are going to test the predicted power of the proposed first and second irregularities on board indices for the enthalpy of vaporization and the standard enthalpy of vaporization. In particular, we're going to use the set of functions proposed in the theorems 2.4 and 2.8, which are these particular theorems that we saw before, for which we are going to have these two sets of functions, the set of function f, that is the one related to this theorem here, in which the particular functional form for the f functions are going to be alpha to the power of p minus x to the power of p all to the power of 1 over p for alpha bigger than 2 over to the power of 1 over p. And the g set of functions are going to be equal to this set of functions here. So note that from this set of functions, we are going to have p strictly bigger than 0, and we can obtain very easily, as I explained before, the irregularities on board index 1 and 2 for the two type of set of functions. And now, once we have computed this, we can easily check the correlation with the chemical property that we want to study. And here we have some of the results. What we see in this figure is simply the correlation between the enthalpy of vaporization, and in panel 1 we have the irregularities on board index for the set of functions f. In the panel B we have the irregularities on board index for the 2 for the f set of functions. In the panel C we have the irregularities on board index 1 for the g set of function, and in the panel D we have the irregularities on board index for the g set of function, the second irregularities on board index. And we can see that the correlation for in the x-axis we will have different values of p, and in the y-axis we have the correlation, and we can see that we get very high correlations for all the irregularities on board index, particular almost for every value of p, for almost for every irregularities on board index, we get correlations higher than 0.9. And the dotted line, what represents is the value of p that maximizes the correlation with the enthalpy vaporization. In the second panel, what we get is we have again the correlation between the irregularities on board index and now the standard enthalpy vaporization. And again, we get for every value of p very high values for correlation, even higher than 0.87. And again, the dotted line represents the value of p that maximize the correlation. Okay. Finally, here we have run a simple regression using the enthalpy of vaporization, running the enthalpy of vaporization on a constant and the irregularities on board indices. We have chosen the value of p that maximizes the correlation, and simply we get we get these results where a is the constant of the regression and b is the slope of the regression. And yeah, this is basically all that I wanted to say about this paper. I hope that you enjoyed the presentation.